Everyone, and welcome to the keynote lecture in the IUPAP 2023. I'm Prajwal Shastri, an astrophysicist and emeritus scientist at the Raman Research Institute and vice chair of the IUPAP Working Group 5, which is organizing this conference. It is my great pleasure and privilege to introduce our keynote speaker, Professor Karen Hallberg. She's from the Balseiro Institute in Bariloche, Argentina. Professor Hallberg is a quantum physicist who uses quantum information-based computational methods to investigate the physics of quantum states and nanoscopic systems, including emergent properties like magnetism, superconductivity. She got a PhD from the Balseiro Institute and has subsequently been associated with several research institutions around the planet, including the Max Planck Institute, Oxford University, the London Center for Nanotechnology, ICTP-3 and the University of Tokyo, among others. She's a member of the Latin American Academy of Sciences, has been vice chair of the IUPAP Low Temperature Commission C5, and is currently serving as a member of the Computational Physics Commission C20. In addition to being an outstanding physicist who has won numerous awards and honors, including the Guggenheim Fellowship and being named an Aspen Ideas Festival Scholar, and many more, which I will not list, she's an inspiration for young physicists in showing the way, embedding her physics practice in our larger context in order to meaningfully address the catastrophic challenges that confront humanity today. She's currently a member of the Argentina Committee for Ethics in Science and Technology and a council member of the Pugwash Conferences for Science and World Affairs, whose work among scholars on the heels of the Russell-Einstein Manifesto for Ceasing Armed Conflict in the World, I need not elaborate upon. In addition, but actually alongside and concomitantly, she strongly advocates and strives for cultural change within physics, for dismantling institutional barriers to women, and thus for a new culture with gender justice, non-discrimination, and equal opportunity. And therefore, her presence and talk in this conference becomes most appropriate. And no wonder too, Wikipedia says that since her childhood, she was always known as Señorita Porque, the Y girl. Karen, the floor is yours.
Thank you, Dr. Prajwal Shastri, for this very nice introduction. It is a real pleasure for me to be here, for me to have been invited. A big thanks to all the organizers, to the IUPAP Working Group of Women in Physics, to the Gender Working Group, the Gender in Physics Working Group of the Indian Physics Association, and to the Tata Institute for Fundamental Research, and mainly to the organizers, to Lilia Mesa Montes, whom I know for a while already, Srubhavati Goswami, thank you very much, and Vandana Nanal for all the organization and all the rest of the team. Thank you very much. As I said, it's a great pleasure to be here. I would really like to be there in presence, but I know, this is very interesting also to be able to have virtual meetings. So I hope we have many young people and mainly young women watching us. And I hope we are able to promote more women, to make them, to inspire more women in science, and also to change the situation of women in science and in physics.
You may be muted.
Sorry, I was muted. I visited Bangalore a couple of times, Bengaluru, at the Indian Institute of Science, and I had a collaboration with Professor Ramasesha on many of the things I'm going to talk to you today. So it was really always very, it was very inspiring for me to visit India, and I like the country very much. So thank you for organizing this important conference. Let me share my screen. I want to start with my
Can I take a minute? I want to Just this little sound problem. Just give me a second to sort it. Yeah.
Yes.
Can you mute this? Just mute. Okay. You are tapping on there, right? Okay. There's somebody else who is on. I wanted to know that.
There is an echo.
Is it better now? No. No.
Is it okay?
I'll just unmute. Is it okay now?
Yes. Is it okay?
Yeah. Klein, please go ahead.
Oh, okay. Thank you very much. So now let me start with my talk about physics. I want to talk to you about quantum condensed matter as a playground for emergent phenomena and complexity. And I also want to convey to you why I'm so passionate about this field. So as Dr. Shastri correctly said, I'm working in Bariloche, which is Patagonia in Argentina, at the Atomic Center in Bariloche and the Balseiro Institute. This is where I live, in the south of Argentina. This is South America, in the south of Argentina, close to the Andes Mountains, close to the border with Chile. There's a campus and a research center that depends on the National Atomic Energy Commission. And so it's in a beautiful place. It's a national park. Here we have some of a photo of the lakes and the glaciers of our beautiful Patagonia. So this is an aerial view of the Atomic Center. You see the lakes and the mountains, and here in the middle we have the campus where we have our physics installations, and also we do research and development on nuclear engineering and other technical careers. Let me first, before beginning, thank my main collaborators. So I have this list of several people on the left from different countries, from the US, from France, from Spain, Germany, Switzerland, also from Tokyo. As I mentioned, Professor Ramasesha from Bangalore, also in Brazil, and some local people in our group. We have the condensed matter theory group in Bariloche. I wanted to stress out my women collaborators, Liliana Rachea, Maria Eugenia Torio, Adriana Moreo, and my students, current and former students from different countries in Latin America, from Cuba, Colombia, Argentina, Peru, Costa Rica. What strikes me here is that, I only had 3 women collaborators out of about 30, so it's between 10 to 12% of women collaborators, and this shows the situation in the field, in this field of quantum properties of condensed matter. So we all know the situation, the amount of women working in physics is quite low, but even in this field, it's even lower. Let me show you, for example, a conference a couple of years ago in 2020. It was an international workshop on quantum entanglement and strongly correlated systems. And this is the group photo. So, you can see very few women. And if you want to try to pinpoint them, there are about 5 of them in a group of 50. So again, we are about 10% women in this field. This is only one particular case, but this is repeating over and over again. So this is why I think conferences like this conference organized by the IUPAP and the collaborators is so important. Let me show you the first IUPAP International Conference on Women in Physics, held in 2002 at UNESCO in Paris, at the UNESCO headquarters. And this is, I am somewhere there, and you might recognize some familiar faces here. So I participated in that first meeting, which was very interesting. And after this meeting, luckily, there were several others held and organized by IUPAP, and this is the 8th meeting. So thank you very much, IUPAP. I think this work should continue. I think we do have progress. It's slow, but it is important to maintain and to continue with this important work. So let's go to physics. Let me talk to you then about what I am doing, about some basic questions we want to solve in my work as a researcher. And this is working with what we call emergence. Emergence in general in physics, and in particular in quantum physics of materials. So what is emergence? Emergent phenomena in condensed matter, let me read these definitions, and material physics are those phenomena that cannot be understood with models that treat the motions of the individual particles within the materials independently. Instead, the essence of emergent phenomena lies in the complex interactions between particles that result in the diverse behavior and often unpredictable collective motion of many particles. This is a definition of the US National Academies. So emergent phenomena means that the more is much more than the sum of the parts. So the whole is much more than the sum of the parts. If we understand correctly or very precisely the behavior of the individual components, it does not mean that we will understand the collective behavior if these individual parts of the system are interacting. So there is a new physics that may arise because we do not handle all the interactions properly. This is a complex phenomenon. This is why it gets so interesting. Another definition was given by Phil Anderson in his article and book, More is Different, where he talks about the reductionist hypothesis. The reductionist hypothesis does not by any means imply a constructionist one. The ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. That means that if we want to study, for example, superconductivity or magnetism, we do not need to know the interaction between the quarks. For example, I mean, we do not need to go to other energy or energy scales mainly to understand what is happening at an intermediate energy scale. At every energy scale, we have our own main interactions, our own order, our own emergent phenomena. So this is very important because if not, it would be impossible. So from the very fundamental physics to try to understand physics at the meso or micro scale will be impossible. And last, I like this thought by Bob Laughlin several years ago, where he says that everything that matters in science now is organizational. The reductionist or fundamental approach has stopped from being useful. So we have to understand organization, and we have to organize information to be able to understand the physics at each scale, in particular, in my case, to understand the physics of condensed matter, which is an intermediate scale. Examples of emergent phenomena in interacting systems. Here there are many interacting systems. Many of them are not quantum, as you see. I mean, but it gives us an idea. For example, an ant colony as the phenomenon. The individual pieces are ants, and the interactions are pheromone trails. So if we understand each ant individually, we will not understand how ants organize and form the different complex behavior they have to organize their habitat, etc. Consciousness, for example, the individual pieces are neurons, and the interactions are neural connections and firing. So the question here, if we understand the individual neurons, we put two neurons together, we understand how they fire and how they interact with each other. We put three neurons together. And the question is there a critical number of neurons above which consciousness arises? Is it a critical number, or is it a question of connectivity? What is the important parameter that we have to take into account to see when this emergent phenomena like consciousness arises? Of course, we do not know what consciousness is exactly. We cannot define it precisely, but we get an idea of what complex behavior might be. Life itself, no? I mean, from molecules and atoms. Crystals, for example, crystals are formed by molecules, and the interactions are intermolecular forces. I give an example, but crystals also form a long-range order and different kinds of orders, and we do not understand completely. Then we can talk about traffic patterns, a school, a flocking of birds, which is very interesting. You might have, seen these beautiful birds and groups of birds flowing and flying in the air, very organized and very beautiful. And this is an emergent phenomenon of how they communicate with each other to form this collective behavior. So in physics, we also have superconductivity, we have superfluidity, magnetism, etc. So here there's a long list of emergent phenomena which it's interesting to study, and they're all complex behavior, even the stock market. Let me give you an example of emergent phenomena in quantum matter, for example, what we call the minimal ice, the smallest piece of ice. So in this paper, published in Science in 2012 by Pradzinski and collaborators, the question they pose is the following: is there a critical number of water molecules above which crystal order emerges? So they did experiments with water molecules where they started clustering a finite number of water molecules. And they found that, for example, when they had 123 water molecules, they still had an amorphous system. Then when they had around 270, 290 molecules, they began to find in the middle of this cluster an ordered pattern. You see here in the middle these hexagons. And then, of course, when they had many more, like 600 water molecules, they could see a long range already arising. So they state in this paper, they conclude that the critical number of water molecules is around 290, 270 with the error bar, above which the crystalline order emerges. So this is, I think it's an illustrative example to see this. So imagine now if we have two main concepts here we have to combine. We have complexity itself, which I mentioned it can also arise in classical systems, so the complexity itself of interactions. But then if we add to that quantum weirdness, because quantum physics, then it gets even more interesting, more complicated, because we have the quantum laws and complexity both together, and this is quite difficult to tackle from the physical point of view. So this is what gives rise to quantum condensed matter, for example. And this is why I think this is one of the most passionate and the most interesting fields where we can do research, because there's still such a lot to know. And this is I want to show you some of well-known results and some of the open results in the field. So materials with strongly correlated electron systems, these are one of the most interesting groups of materials, because they have this emergent phenomena and they show very interesting phenomena like magnetism, superconductivity, superfluidity. And for example, metal insulated transition, ferroelectricity, etc. I mean, many of the interesting phenomena and also interesting for applications arise or exist in the materials with strongly correlated electrons. This is where many-body physics is important. I mean, we cannot study these materials by simplifying the behavior of the electrons, as studying, for example, the physics of one electron, as we do in semiconductors or in copper or noble metals, where we know the energy bands of one particle, and then where we put many particles in the system, the energy bands do not change. When we have interactions, depending on the number of particles, the whole distribution of energies will change. So it is a complex situation where interactions play a crucial role. Examples of many-body physics arise in Fermi and non-Fermi liquids, like, for example, in low dimensions and close to quantum critical points. And this can be seen, for example, in the fractionalization of the electron and in charge and spin separation. This is interesting because we know that an electron has charge and spin, but when we have interactions, charge and spin degrees of freedom can move independently. Another example is, for example, the broken symmetry phases and with hidden order, like in liquid crystals, how this order arises, or different phases with topological order, like the fractionalization of charge in the fractional quantum Hall effect, where even the charge is fractionalized, and it's not one E, but it can be a fraction of E. We can also have fractionalization of spin, where we have, for example, systems with spin 1 that can show excitations of spin 1/2. And when we do not have spin 1/2 systems, so this is due to the interactions, we can have fractionalization of orbit and spin degrees of freedom, as I said, and we can also have the existence of magnetic monopoles, which I'll show you in a while. Also, interest in physics like superconductivity, superfluidity, which are quantum coherent states, are very interesting from the basic physics point of view, and also, of course, for applications. Critical phenomena like scale invariance independently of the microscopic components. Scale invariance in physics, it has to do with phase transitions. It's a very important and very interesting phenomena. Then, of course, cold atoms that show metal insulated transition, and the existence of new quasi-particles, because we know that we have particles, for example, from the fundamental physics and hadrons and fermions. But when we're looking at condensed matter, we can have new quasi-particles that behave like particles at this scale of the condensed matter physics. Let's talk about the fractionalization of charge of the electron. What happens, let's see an example when charge and spin separate. Here we have an example, we have a one-dimensional system. As you see, the first row is a one-dimensional system where we have spins or electrons. Let's think of let's say a model in one dimension. So we hit it with a photon, and we extract an electron from the system, so we produce a hole. This hole can move freely from, towards the right in this case. If you look, time goes down. So the hole has its own dynamics, and then towards the left, we're left with not with an antiferromagnetic, but with a ferromagnetic alignment of the spins, and this is called a spin-on. So it is an excitation within the antiferromagnetic background of the spins. This spin excitation can also move towards the left because we have spin-spin interactions. And as you see in the last row, we have this spin-on moving towards the left and the holon moving towards the right. So here we have the holon takes charge excitations and the spin-on takes spin excitation. This has been also observed in a real system in this paper in Nature, in a quasi one-dimensional system with strontium, copper, oxygen. So this is very interesting because we really have a fractional charge and spin excitations. This has been observed in, for example, high-temperature superconductors, these Behat and Fabre salts, copper chains and ladders, carbon nanotubes, one-dimensional cold Fermi gases. With all these experimental methods, I won't go into, but then you would have access to my talk. It has also been, spin and charge separation has also been observed in ultra-cold quantum gases, for example, in a quasi one-dimensional system of cold fermions formed by 1,000 lithium atoms. So lithium-6, each atom is a fermion because you see that it has an odd number of neutrons in the nucleus. So it has a net spin 1/2. So it behaves like a fermion. And in this work, Recati and collaborators formed a one-dimensional version of these called fermions, and they excite with lasers. They excite what they call spin, and they excite the charge degrees of freedom with a laser in the middle of the one-dimensional chain. And they observe, you see in part B in the middle, at 0 temperature, they produce the excitation, and then we see that the spin, which is this intermediate curve, moves out after a certain time, and the charge also moves at a faster rate. So the charge and spin degrees of freedom are observed to be separate. This was a very nice manifestation and observation of charge and spin separation in one-dimensional cold fermions. several years ago, when I was doing my PhD, we did a calculation with my advisor and a collaborator on a one-dimensional interacting system. So mimicking, for example, similar to what was done in cold fermions, but this was one of the first works. This is 1993, so several decades ago. And this is a one-dimensional interacting system, which is called the Hubbard model, where we have electrons moving and strongly interacting. When we have two electrons on one side, we have an interaction. They pay an energy U, a Coulomb energy. Okay, so then we look at the dynamics of this quantum system, and we measure, for example, the charge and spin degrees of freedom. The charge is adding the local densities, and the spin is subtracting the local densities of spin up minus spin down. So we calculate with numerical diagonalization the ground state. Then at time 0, we add an electron to the system with a certain momentum, and then we calculate these mean values of charge and spin as a function of time. When there's no interaction, when U is equal to 0, to the left, we see the top is the charge density and the lower is spin. So we see the charge and spin, they move in a wave packet coherently towards the right of the system, and both of them are exactly the same excitation. Of course, the wave packet deforms because the dispersion relation is not linear, but both excitations are exactly the same. If the interaction is very large to the right, again, we create the wave packet here, and as a function of time, we see that the charge, which is the top curve, is moving faster towards the right than the spin. And this is because the charge density has a different dynamics and is completely independent to the spin dynamics. So this was an interesting result. This was done just to show you that when I was doing my PhD, I published this paper, and then a couple of months later, I defended my PhD with my two children, Kevin and Tanya. They were quite small in those days, 93, just to show that, I mean, it was completely possible to do my PhD with two children. And of course, I mean, this is the message that a physics career can be done with a normal life too, and so I'm very happy with my family as well. Let's go back to physics then. I want to show you that also, I mean, this complex behavior of the separation of charge and spin has also been simulated by a quantum computer called Sycamore, which is Google's quantum processor. The Google's quantum processor is a collection of superconducting circuits where the bits are superconducting fluxes in this arrangement that is shown here, for example. So they, in 2019, they claimed that they reached what they call quantum supremacy, or the quantum, they were above the quantum breach because they could calculate a random number in 200 seconds versus what they claim was 10,000 years in a classical computer to generate this random number. However, IBM then came with a counter argument saying that it was not really 10,000 years, it's much less. But in any case, they were able to control very precisely the noise and all the problems that arise in quantum computers. So it's a very promising quantum computer. This, of course, I mean, as for applications, there are many applications that can come from calculations with quantum computing, like drug design, new materials, climate science, finances. Optimization problems is one of the most important applications, cryptography, communications, etc. So to show the power of this quantum processor, what they did, among other simulations, is observe also the separated dynamics of charge and spin in the Hubbard model, which is what we did. So they mention it in this paper, they cite it. And this is, again, they show they have a one-dimensional array of 16 qubits, but they have more than 600 qubits around this system to correct the errors. So it's not a trivial task to correct the errors in a quantum computer. In any case, they simulated the system where they had a one-dimensional interacting system, and they measured the charge density and the spin density, the charge in blue and the spin in red. And they also found the dynamics for different times. At time 0, they create a wave packet, and then they simulate the evolution of this wave packet, where they see that the charge travels faster than the spin. The charge is blue and the spin is red. So this is something seen in a different system where one can also find this phenomenon. So now let's look at another fractionalization, and in this case it will be of magnetic monopole. We're going to create magnetic monopoles with interaction, and this is anti-intuitive because we know, in principle, I mean, from the basic causes of magnetism, that magnetism cannot be separated into monopoles, but this can be achieved in an interacting system. So let's look at this real system, which is based on dysprosium and titanium oxide. It is a collection of tetrahedra, corner-sharing tetrahedra, and in each tetrahedron we have in the ground state, as you look at it here, top left, we have in one tetrahedron, we had two spins pointing inwards and two spins pointing outwards. In the neighboring one, we also have the same situation in the ground state, two spins in and two out. This is the ground state. Then if we get the middle spin and we flip it, we go to the B part, the top right, and we find that this tetrahedron marked in blue is a spin excitation with a positive outgoing spin. So here we have 3 out and 1 in, and the red is 3 in and 1 out. Okay, so this would be the negative part of the dipole. And then if we continue, for example, at this right edge, if we flip now the spin, if we flip it outwards, then this red tetrahedron will be neutral because it will be in the ground state, but the neighboring tetrahedron will be red because it will have 3 in. And in this way, we can continue propagating the spin excitation farther and farther away from each other, and then we form like a string here where we show the blue is up here and the red negative spin excitation is down here. So we were able to separate the spin, the magnetic monopoles in this system, and this has been observed in this paper. So this is also a new fractionalization physical effect due to interactions, spin interactions in this case of the system. A very important example I also wanted to show you is the high temperature, high TC superconductors. These were discovered by Bernos and Müller at IBM in Zurich in 1986, and it led to a Nobel Prize in 1987. So only a year after that, because it was a very important and striking discovery. They were working with complex ceramics and interacting systems based with that had as components it had rare earth and different kinds of materials, especially copper, oxygen, and transition metals. So here there is, for example, what they found is that the superconductivity, this was in 1986, so in the middle of this graph, in 1986, here lanthanum, barium, copper, oxygen was the first discovery, and the critical temperature was around 30 Kelvin. But before that, all the superconductors had much lower critical temperature. So this was a completely new discovery with a critical temperature to superconductivity that was quite high. And then after that, you see towards the right of this figure, there were the discovery of many other complex materials, all of them strongly interacting, that showed high temperature superconductivity. Here to the right, I show the crystal structure of one of these materials, which is IBCO. yttrium, barium, copper, oxygen, where we have copper oxygen planes, we have the yttrium in between the planes, etc. So now we have to understand this. We want to try to see why we get superconductivity. And to date, we do not understand why superconductivity arises in this material. We have so many theories as theoretical physicists working in the field. This is a joke, but I mean, there are many, many different proposals for superconductivity, from the pairing mechanism, because for superconductivity, we need a pairing of electrons, and there's no single comprehensive theory of the superconductivity in these materials. So this is why, because it's very complex, because there are many physical processes in between, and it's not that we lack computer power, but this is an emergent phenomenon we do not completely we do not understand. We have magnetism, we have orbital ordering, we have phonons, magnetism, electric interactions, etc. So I mean, putting all this together is an extraordinary task. So to date, high TC is not understood. So 40 years after its discovery, we're still waiting or looking for the mechanism. We don't even understand the normal state well, because high TCs are not not easy to understand. They're not normal conductors or insulators, and it's a very complex normal state. The discovery of high TC catalyzed research in systems with strongly correlated electrons, like are right here, and many body systems. It's one of the most complex and fascinating systems we encounter today, because it's really complicated to grasp and to understand. So this is now brings me to what we call the concept of complexity. So complexity is a property that grows exponentially with system size. So we have an exponentially large number of states and of physical and of interactions in the system, and this is not only it's not wise to resort to computer power alone to understand this, because as it's exponential, it's immediately it gets out of control. The only way to understand this is by organizing the information and understanding the information in the system. So we must optimize the information to try to understand it. So we have to we have to keep the most important states, and we have to get rid of all the states that are not important to understanding the problem we're studying. This is why it's important, what I write here, to understand we have to do quantum optimization using quantum information. We are doing that. This is my current field. Let me go to an example. So the example would be in a one-dimensional Heisenberg model, which is a very simple model that has exponential complexity. I found this very nice artistic interpretation of complexity and exponential complexity of the Cayley tree or Bethe lattice. As you see, the tree from every branch, we get let's say 2 or 3 sub-branches, etc., etc. So this immediately grows exponentially, like this tree. Now let's think about the Heisenberg model. The Heisenberg model, it can be in any dimension, it's complex, but let's look at one dimension. So this is a spin-spin interaction between site I and site I plus 1. We have a one-dimensional array of spins, 1/2. So in each site, we have a spin 1/2, a quantum spin. It can be up or down. We have 2 degrees of freedom. So this is also called a qubit. Okay, so it's a qubit. If we had 3 degrees of freedom, it would be a qubit. But in this case, we have 2 degrees of freedom per site. So if in every site we have 2 degrees of freedom, if we have 2 sites, we have 2 times 2, so 4 degrees of freedom. And if we have n sites, we have 2 to the n different states we can form. Okay, so it's exponentially large in the number of sites in the system. So if we want to calculate this exactly using matrix Hamiltonians and matrix operations, all our operators would be matrices that are exponentially large, because it would have 2 to the n states, and this is impossible to graph. To date, we can calculate in classical computers 28 sites or 30 sites. That means we have 2 to the 30 states in the system. So it's not necessary to use all these states, and this is where something, an important development that was done some years ago. I'll tell you now, but before that, let me convey a thought by John Preskill, where he says that he talks about the importance of using quantum information to optimize calculation. This is a new interesting perspective in quantum mechanics. John Preskill said that the most challenging and interesting problems in quantum dynamics involve understanding the behavior of strongly coupled many-body systems. And better ways of characterizing the features of many particle entanglements may lead to a new and more effective methods for understanding the dynamical behavior of complex quantum systems. So it's important to find better ways of characterizing these features, like John said. So in 1992, Steve White in Irvine in the US, he came up with a new method, which is called the density matrix normalization group, which uses quantum information to keep the most relevant quantum states in the system. So we do not keep all the states, the 2 to the n states. We only keep a very, very small percentage of states. And how do we choose these states? We choose them using quantum information. That means, for example, let's look at a system like the one here in the top left. We have a big system, let's say a very long chain. We can calculate if we can calculate the ground state of that system. We have, for example, what we call a pure state in quantum information language. Doesn't matter. I mean, this is a technicality. And then we can calculate what is called a density matrix on a part of the system. So we partition the system, and in the red part, for example, we calculate what we call the density matrix. The density matrix is a projection of the wave function into part of the system, and then we would have matrices in a part of the system, and the matrices are much smaller, than, of course, than the matrices in a large system. We diagonalize this density matrix, and the important property here is that the density matrix has eigenvalues. The eigenvalues are the probability of finding the corresponding eigenvector in the state we're looking at. So what we do is we only skip the eigenvectors of the density matrix that have largest eigenvalue. This is a technical thing, but I mean, maybe some people are working in this, so they might understand it. So it is simple. We calculate the density matrix, we look at the eigenvectors with largest eigenvalues, and we keep only those eigenvectors. So we don't have to keep the whole universe of eigenvectors of the system. And we do this, and we grow the system, or we grow the number of states, etc. And in this way, we can control the importance of the quantum states we're keeping. So this has been a very important development. This led to tensor networks, and now many physicists are working on tensor networks because this is the way to treat correlated systems, and this method turned out to be very precise. What I did during my postdoc is cited here. What I did is to extend this method developed by Steve White to the calculation of dynamical properties in quantum systems. And then I wrote a review on the system, the method, several years later. What we also did with collaborators is extend this to other very well-used and well-known methods for correlated systems, which I'll tell you very briefly in a while. Why? We want to calculate systems like this. I mean, this is a normal Hamiltonian, the 3-orbital Kanamori Hamiltonian. I mean, doesn't matter, but our Hamiltonians, of quantum Hamiltonians, or interacting systems look like this, where we have Hopin terms, we have chemical potential, we have Hopin's hybridization between different orbitals, and we have interaction terms like this VI. The interaction terms are usually local or first nearest neighbors, And they are very complex. They have Hubbard U, so on-site Coulomb interactions. They also have interorbital Coulomb interactions, magnetic interactions, Kondo interactions, etc. So we have complex things that looks like this figure here. We have different interactions in the system. How do we tackle these very complex models? So one method, we can use a DMRG directly, but we can also use another method, which is called the dynamical mean field theory. Sorry for all the acronyms. This is DMFT. And so this is dynamical mean field theory. It was developed several decades ago by Kotler, etc. Also Professor Dieter Volhard and Antoine Georges. It's a very efficient method to calculate correlated systems. So what you do is you have a correlated crystal, and then it's a mean field theory. So you pinpoint one site, and then you calculate the effective medium interacting with this site, but you do this dynamically with Green's functions, with response functions. So you want to calculate the self-energy. I won't go into detail, but it's a very efficient way of treating the interactions on the site. Now, at some point, one has to calculate the dynamics of this effective complex impurity in an effective medium. How do we calculate that? This is where we come in with the DMRG, with the density matrix normalization group. So now we're combining two very powerful numerical methods and putting them together, and we get very good results for this. So we're combining the very well-known dynamical mean field theory, and we're bringing in the DMRG, the density matrix normalization group, to solve this effective impurity. So then we come up, our impurity, this is called the impurity solver. There have been very many different impurity solvers for this DMFT. But ours turns out to be one of the most precise, because within our method with the DMRG, we can calculate dynamics in the real energy axis at all energy scales with arbitrary interactions. We don't have the sign problem of Monte Carlo. We can look at large baths, several orbitals, etc. These are also technicalities, but it's really very promising as a numerical method. And then we have things like this. We finish up with our method in a complex structure. We have to code, and that's what we do here with our group. We code this impurity solver in this other DMFT, and we have several orbitals with effective bath, and our Hamiltonians look like big things like this. And this is what we code and we calculate with the DMRG. And we get results like this. For example, this is a simpler case, which is the two-orbital Hubbard model. I'm only showing, just as an example, densities of states for different parameters. It doesn't matter too much, but for example, if we have the densities, in the two-orbital Hubbard model, we have orbital 1 at the top and orbital 2, the lower orbital. And we have hoppings among the orbital 1 and orbital 2. And we want to see what arises here. Well, we found quasi-particles in the system. Quasi-particles of this form. We found, for example, that we have a hole in light blue and a doubly occupied orbital. And this complex quasi-particle moves in a quite coherent way. So this, what we call holon-doublon quasi-particle, has its own dynamics. You see here we have a holon-doublon, and here we have another one where we have a holon in orbital 1 and a doublon in orbital 2. And we did find these quasi-particles. They hadn't been observed before, thanks to the precise numerical methods we were calculating. So we observed, for example, densities of states. These are projected onto orbital 1 and orbital 2, the different colors. And when U is equal to 4, we have a large interaction. The density of states shows, you see it's 0 close to omega equal to 0. I'm looking at the lower right. And this means that we do not have states close to the Fermi energy. So that means we have an insulator, because we have a large gap. You see, this is energy, omega, and we have a gap in the Fermi energy. That means that we cannot excite charge in the system. But when we lower the value of interaction from U equal to 4, from U equal 4 to U equal 3, here in the lower left, we find a large density of states at the Fermi energy. That means we have a metal. This red means that we have a metal in orbital 1, but we have a gap in the black one. It means we have an insulator in orbital 2. But these new peaks we find in the middle of the gap, you see these black peaks here, these are a fingerprint of the quasiparticles existing in this system. Okay, so these conspicuous peaks we find within the Mott gap are an important feature that hadn't been seen before, and we call them the quasiparticles. So this is an example of how this is an emergent behavior, because in this complex system, we have complex quasiparticles that are formed by 2 electrons or a doublon and a hole, and these move together coherently and interact within each other. Now, we would like to understand how these quasiparticles interact, what is their dynamics, etc. Yeah, and even maybe if there is an attraction between these quasiparticles. So, well, now let's go back.
Karen?
Yes, thank you very much. And I'm about to finish now with my last caveats about the situation of women in physics. I want to get the big picture. So here I want to talk about the Nobel laureates in science. What I did is this is the updated number of women that got Nobel prizes in science. So I only looked at physiology and medicine, at physics and economics. And chemistry. Okay, so the numbers are striking. We only have 12 women in physiology and medicine out of 213 men to date, 4 women in physics out of 218 men, 2 women in economics out of 88, and 8 women in chemistry out of 183 men. So in total, we have 26 women laureates in the Nobel laureates in science out of 702 men. This is a very striking situation. But we don't only have a problem with women in physics, or women in science, in this case, in particular women in physics, but we also have a problem with equal opportunities and development in different regions of our world. If you look, for example, at the Nobel laureates in science in Latin America, one can do this with other regions, of course. Latin America, we have very few Nobel laureates in science. For example, Argentina has 1 Nobel laureate in chemistry and 2 in medicine, so we have 3 in science. Mexico has 1 Nobel in chemistry, and Venezuela has 1 Nobel laureate in medicine. In total, Latin America has 5 Nobel laureates in science, all men, all of them men, or out of 721 Nobel laureates in science in total. It's 5 in 700. So this is really something we have to think about. There are many problems we still have to solve in science to be more inclusive, to be more just, and to give equal opportunities. So I want to leave you with my last reflection. There's a lot to do. The situation is changing thanks to efforts done by the IUPAP and other people and organizations, but we still have a long road to go. So there is still a long way ahead. And so my final thought is that my dream is that one day, thanks to the strong interaction and collaboration of many people and institutions, a new reality in physics and science will emerge, in which any kind of bias will be eliminated and where complete equity and inclusion will be achieved. Thank you very much.
Thanks very much, Karen, for that absolutely wonderful presentation and for the dream, which we should all carry forward. So there has already been a question in the chat earlier by Farida Fassi, who says, what is the underlying physics behind charge and spin separation? Could the electron-electron interactions in the presence of a magnetic field play a key role in this concept?
Yes. Well, in the presence of magnetic, we do not need a magnetic field to produce charge and spin separation. This charge and spin separation arises from the interaction among electrons. In this case, I showed is a very strong local Coulomb interaction. So we do need strong interactions to be able to see the charge and spin separation, but we do not need magnetic field, although it can survive in a magnetic field, of course. I mean, this is also, it would be also interesting to see, because the magnetic field only produces excitations in the spin, if we're looking at the Zeeman magnetic field, but the magnetic field can also produce a phase change in the electrons. If we have, for example, an Aronoff bomb ring, we have a one-dimensional ring which is pierced by a magnetic field, we can also see how the phase of the magnetic field couples to the phase of the electrons, and we can see very interesting coupling phenomena and the separation between charge and spin.
Thanks for that. I don't see questions by the others, so I'll take the second question by Farida Fassi, which is, the density matrix tool describes and analyzes the quantum state. What about mixed states?
Well, thank you. That's a good question, very good question. We also analyze people in this community. We're also using mixed states. What does it mean? For example, we have a quantum system. Let's think about a one-dimensional Heisenberg model. If we look at the ground state, that's a pure state, or we can get any state of the system, and it's a pure state, only one. But then we can also have a mix. It can be in a mixture of states. It can be in state 1, state 2, state 3. For example, if we put temperature, it's in a mixture of states, and it has the Boltzmann weight, okay, in each state. So now we can also calculate the density matrix, but not looking at the pure state, but looking at the mixed state. And this gives us another density matrix, which will reflect the physics of this mixed state, and it will give us quantum information of this original mixed state.
Thanks. There's a question from Francesca Okeke. She asks, is there any way or ways quantum physics affects lives?
Lives? Yeah, it does affect my life because it gives me to eat. It gives me passion to work in that sense. But let's see. When plants plants use it a lot when they have all the process of life, or even us. I mean, the processes at the level of molecules. This is something. It's interesting because at some level, of course, we have the molecular quantum processes, but then, if we want to calculate, if we want to look at biologists, for example, they want to look at what happens with DNA, the processes at the cell level. We do not need to understand. We do not need to go to a reductionist interpretation of what is happening in the cells. We do not need to understand the nuclei. Some cases it might be, because I mean, sometimes it might have an effect, but one has to be able to separate and to simplify the information we're using. So in some processes, we do have the influence of some at the molecular level, but it is not necessary to use quantum physics to study most of the biological interaction. But so, well, I mean, each science, each area results to its own physics, to its own laws. In this case, the biological physics.
Okay, the next question is from Usha Devi. She says, most of the whole pure states can be determined from its parts, a resultant quantum information theory. Do you have any comments? She adds that parts being reduced density matrices of the whole pure state.
Yes, yes, this is exactly what we are doing. The reduced density matrix is calculated in part of the system, and we can reconstruct the state of the full system from this reduced density matrix. But the main message, the main physical the main part of this method is that from all these physical states or the part of the system, we only stay with a few of them. We don't need to stay with all. So we would not be able to reproduce exactly the state of the whole system. We will reproduce it partially. It's not exact, but it's a very exact approximation. It's a variational approximation. So we do not keep the whole amount of states of the density matrix. We only keep, let's say, out of 10,000, we stay with 100 states, and this is enough to describe the system very precisely. It's not exact, but it's very precise, and it's useful because we can go to much larger systems.
Thanks. So Vandana Nanal asks, can you comment on the potential of the density matrix to for predictive phases / materials?
Yes, this is a very important area and a very important question, because we want to predict behavior. We would like to do materials by design and say, well, if you gather these and these atoms with these interactions in this order, then we will get superconductivity. Or if we do this other thing, we will get magnetism, etc. Having predictive behavior is very important. Now, the DMRG, together with these other methods, help us understand the system, but they haven't been good enough yet, or we haven't been good enough to come up with a theory, for example, of superconductivity. I can't give you a predictive behavior of what materials will superconduct and which ones no. I mean, there's a very general picture, but still it's not precise enough to be able to give you an answer, a predictive answer. But it's one of the important methods, together with Monte Carlo mainly, that are used for quantum systems. And I think we are on a good track, but well, it's evolving slowly because it's very complex.
Thanks. Lorena Salazar asks, can you mention about how much time do the calculations take and how this has changed with the evolution of computers?
Yes, the time, thank you, Lorena. The time, well, it takes quite a lot of time, but much less time than if we were calculating things exactly. For example, if we're calculating now with my student, she has coded part of this DMRG for. We're looking at the 2-orbital model. For example, for let's say 40 sites, it takes about 2 or 3 hours to calculate the ground state and the dynamics of CPU time at our computers, which are normal. I mean, they're not a supercomputer. Things have improved a lot because we use a lot of gigabytes in our memory. And I remember when I was doing, I mean, a couple of decades ago, thinking of having 1 gigabyte as RAM memory was impossible. And now we're using, we can use 100 or more. So in this case, and even the speed has increased. This is good. Now, when we have quantum computers, this will be good. I mean, but this is still it's a big hype, quantum computing. But it will help. It will help. For example, maybe in even less than 10 years' time, we will be able to have quantum computers to simulate materials, because it's a quantum system that is really simulating a quantum material. So it's like cold atoms. Cold atoms also serve as an experimental field to look at quantum interactions. It's another way of simulating other materials. So in that, we're waiting for, I mean, this quantum computing. Now we have one result I showed here, and this was interesting. And this in some years' time will improve.
Thanks. Rohini Kodbole says, I guess it is also a question of distance scales that one is investigating the science. This was about your comment on biological systems not needing knowledge of nuclei.
Yes, exactly. It's a question of scale, mainly a question of energy scale. But then you can also compare the scale, for example, of the scale of the particles. I mean, what is the de Broglie wavelength of particles? So when the particles are very massive and they have a very short de Broglie length, then they're treated as classical. But then if you put them together and their wavelengths start and getting entangled, then you have to treat the system with quantum mechanics quantically. So the scale is very important. Energy scale is very important. We don't use MEVs, mega electron volts in condensed matter. We use electron volts. Okay, so this is a completely different energy scale, and this is where this is the main message of emergent of my part in emergent phenomena. Every energy scale has its own important information that has to be analyzed, and each energy scale is a different way of organizing information. If we really, it wouldn't be wise to again to study an intermediate energy range of a few electron volts by using the physics that arises of the subatomic particle physics of hadrons, for example, because we would be overshooting, and it's not necessary. We would never be able to understand the system if we are so reductionist.
So we are coming to the end of our time. I will pass on one last question by Zacharias, who asks, have you compared your results with those of the SC-DFT from Hardy-Gross group, including Cesar, Prieto, Bariloche?
Well, because yes, thank you for mentioning that. He's a colleague of mine here at our group. Well, they are looking at different systems. They're looking mainly at semiconductors, and they're using DFT. So it's DFT is another acronym. So it's density functional theory, and this is also very important. The density functional theory is also very much used for models. I didn't mention it here, but this is used for models that are not strongly interacting. So DFT works very well for semiconductors, etc., or for other materials that are not strongly interacting. Because if you put interactions, if the interactions are very strong, DFT is not good enough at taking interactions. So this is why what we are doing now is, with our methods, we're getting information for the energy levels from DFT, and we're adding interactions into those energy levels. So this is getting the good part of DFT that gives you a very good energy levels and adding interaction. DFT is very good for modeling materials. So this is how things start getting together, and this is our next project with my PhD student.
Well, thanks very, very much for both the talk and the lively discussion, all the answers to the questions. Thanks very much, Kathy.
Thank all of you. Thank the audience who I'm not seeing, but thank you very much for being here. And thank you very much, Prajwal, and all the organizers. It's been a really big pleasure.
Thank you, Karen and Prajwal, for both for the wonderful talk and for wonderfully conducting the session. And really hope to meet you sometime in person and listen to the things. Yeah, sure. So thanks again. And we will now close the session.